Alright, this is Anthony Wise for MathLogic 5154, problem presentation, and something I've learned. So for the first one, this is the problem presentation on page 75, exercise 1.5 in math models, models and ultra products, an introduction, but this is the Bell and Slompson book. So 1.5 is let H be an isomorphism between U and B, and show that H is an elementary embedding of U into B. So this is a fairly simple one. I did this one because it took me a while to understand this concept, and so this kind of just solidifies my own understanding, and I hope it helps somebody else too. So I'll try to post this in the discussion forum so everybody can see it. But anyways, here's my proof. Please let me know if I wrote my notation wrong. I welcome criticism, especially of that nature, so I can get it right. The first part is if H is isomorphism between U and B, which is what is given, then there exists a phi, right, for all the A's that are in U, such that there is an H of A that is in B. And that's just basically saying that this formula phi, you take an element A, all of the A's, A0 all the way to N, whatever they are, such that when you take that, map that into B through this isomorphism, which is one-to-one and onto, you get this result, which is the H of A, which is a value, right, of any of the A's that is in B. So that's a requirement, because you're mapping one-to-one, so for every one element that's in U, there's one element in B, and it's onto, which makes it straight from U to B. Okay, so then the second part is by Lima 1.1, page 74 in the book, and by substitution, you get this. You basically, the Lima basically says that U, and I can't remember what this symbol, it basically means equal, but it's that way. It's onto the phi, right? Actually in the book it's called sigma, but if you substitute this phi in here, then you're saying that for every phi that has an A starting at 0 all the way through N, right, all the A's that are in phi that are affected by phi, right, if and only if that B has those same phis, right, but they are H of A, there's your H of A, but this is 0 all the way through H of A N, which is the last nth case, right, and thus, because these are here as laid out by phi, because H is one-to-one and onto, thus H is an elementary embedding of U into B. I probably muddled that up a little bit, but I welcome an easier way to say that, but that's my proof. So then the next one is this problem presentation for the logic of thermostatistical physics. There's really no examples or problems in this book, especially in chapter 16, right? Because it's just kind of going over the philosophy of between idealizations and approximations, and when you can simulate and when you can't, that kind of thing. But anyway, so the best I did was ontic idealization refers to a real or factual, and in this case means that each individual idealization is also insulated from each other, that each other that hold their truth value without affecting one another. So basically, if you had two, right? Here we go. If we had two, this truth value, or not truth value, this truth idealization doesn't affect this one over here. They're completely separate. Okay, and then epistemic idealization means that each individual idealization relies on another. They act as a string. So if one falls, they all fall, right? Like the Three Musketeers almost, right? So then basically I had this question. It seems to me that coming from a macro view and then zooming into a micro view, So if you're looking at the whole universe and then you zoom all the way into the atomic level, right, there is this transition between this epistemic view to the ontic view. I'm probably saying that wrong. But where's the threshold, right? Where's the line in the sand that says you change views right here, you know? And do these two viewpoints mesh so well that there is no discontinuity between the two, or is it a jumping off point that is negated to reduce error? I don't really have an answer for this. I wanted to pose this question to see what kind of response I would get out of it, especially in the discussion forum. This is kind of a big deal because, if you think about space and time were viewed as two separate things, Newtonian, Galilean, that kind of mindset, and then Einstein went and did space time, right? I think that's the example in the book, and he merged the two. Then really the only time that this becomes an issue is when you're getting really close to the speed of light, and the time and space start to change, and they depend on each other, and they change in specific ways. Sometimes they're not intuitive, sometimes they are. But is that the only point in this idealization structure that we're talking about in this book? Is that the only point when that really matters? When you get to the microscopic level, the atom level, and you're talking about things that are moving at the speed of light, okay, obviously you're going to be doing this top one, I think, right? But when you're talking about the whole system, the whole universe, you're going to be doing the second one because everything kind of depends on each other. But where is that line between the two? I kind of think that it's right here. There's a discontinuity. It's like you use one all the way up, and then as soon as you get to this certain point, it's like, oh, the other one takes over, and then you just go this little bit, and that's it. I could be completely wrong about that. Anyways, all right. So then the last part of this is something that I learned, and this is something kind of funny. Per the reading, the approximation of pi, as an example on 526 gives a curious validity to how close is close enough. Is 3 close enough? Is 3.14 close enough? Is pi to the 1/1,000,000th decimal close enough? Yeah, I think it depends on what level you're trying to get to. But the other thing that made me think about this, or that kind of taught me something about it, was it gives this example about the electron microscope and the programs they use to run simulations, right? So you're studying something at the atomic level. You're studying these interactions, and you're trying to see, what kind of atoms you're getting out of the backside after you fire them at each other, and they either terminate or they don't, right? And you run these simulations. Well, you have to consider that a particle accelerator, electron accelerator, that you need in order to do your experiment is not going to be readily available. It's not like you can go down to Lowe's and get it. So then that begs the question, how much simulation is actually appropriate? Do you simulate all the way up to, you're starting to get really, really good results in your simulation, and you're starting to see correlation between your work and some other people's theses or experimental work in the field? And also that is also coupled with, at what level do you do that work? Because a supercomputer to crunch these numbers for you to do the simulation is also not going to be cheap. So you've got to do the simulation at a certain level. Is it between those two values somewhere? And you've got to do it within a certain resource value stream that will allow you to be able to get the experimental data you need, whether it's from simulation or actual data collection from the field from using a particle accelerator. But then you've got to factor in time. You got to factor in when you actually have funding to do that. how much the simulation is costing you, all that kind of stuff. So it's funny that that all those things play in to something so simple as like this. Because if you're trying to approximate pi and you're trying to get as many decimal points as you can, that's a freaking massive computer that's going to get out there and do that calculation for you. Do you have access to that? It's just something to think about. It's something that reading this really taught me was, where do you stop? Where's the level that you stop at? And can you justify that? And is that acceptable for the level of research that you're doing? So anyways, I hope you got something out of this presentation. If you have any questions, like I say, contact me. I'm easy to find on the email. I think there's only like 8 of us in the class. So anyways, happy summer.